Okay. All right, so today what we're going to do is I'm going to talk a little bit about mesh refinement, okay? How this process works, all right? There's no one way to do this. There are many papers that have been written on mesh refinement, but the concept is as follows, all right? So I'm going to title this thing mesh refinement, or loosely, mesh refinement. So I've been doing this with Redao just because it has a nice structure to it, so it makes it fairly straightforward to do it. But the way we do mesh refinement is as follows, is that it's an iterative process. So mesh refinement is an iterative process. What I mean by iterative is that you start with an initial mesh, and then you have to decide how you're going to modify that mesh in such a way that you move the next mesh closer to a solution that meets your accuracy tolerances, whatever those accuracy requirements are, and you stop the process once your accuracy, the desired accuracy, has been met. It's very similar to what happens when you integrate a differential equation using an adaptive step size method. Have any of you ever used adaptive step size methods to integrate differential equations? If you use like a Runge-Kutta method, or Runge-Kutta is usually the common way to do this. You take a step of a certain size, and then based on that step, you decide whether or not the solution you have at the next step whether you can take a bigger step the next time or a smaller step the next time, depending upon how quickly the solution is changing. And so that's how adaptive step size methods work. You don't take the same length step every single time, because in certain regions of a trajectory, it may be that you can take giant steps and get very accurate solutions, and in other regions you have to go through them very, very slowly in order to be able to make your way through it. That's typically the mathematics of adaptive step size has to do with the truncation error based on whatever the step is that you're taking. This is not that different from it, but it's based on collocation, so it has a little bit of a different flavor. Okay, so the way it works is this: start with an initial mesh. Okay, this mesh could be anything, all right? But because of the way we've done it, this mesh is on -1 to +1, okay? So I've picked a mesh. I don't know what this mesh is. It could be anything, right? So this is S1, S2, ... up to Sk minus 1, and this, of course, is S sub k, and this is S sub 0, right? What we do in each of these meshes, so this is going to be mesh interval 1, 2, 3, 4, 5, or whatever this is. We pick a polynomial. We pick a degree for the polynomial. So we pick n sub 1 Redao points here, n sub 2 Redao points here, all the way up to n sub k Redao points in the last interval. This is n sub k minus 1. Okay, so now we have chosen the locations of the mesh points, and we've chosen the degree of the polynomial in each of those mesh points, right? So then what you do is you solve the nonlinear programming problem on the given mesh. Now, the key step in this is once you've solved it, now you have to assess the accuracy of the solution. Now, this is what is the hard part. The next thing is really easy. After you do this, the next thing is a piece of cake. So I'll write it down, and then you'll say, okay, well, that's a real piece of cake. So, which is that you assess I should actually say this is 2 steps really, is assess the accuracy of the solution, and then determine the new mesh. And then you solve the problem, and then you go back to step 1 with the new mesh. And then you repeat this process until you meet your accuracy tolerance, right? Now, it's these 2 steps right here that are the problems. Okay, so the way you would, or to say a way to do this with Redao points, and it's not by no means the only way to do it, but it's one way to do it, is that consider the solution in mesh interval sk minus 1 to s sub k. Okay? So here I am. I'm sitting at mesh points. I'm sitting between mesh points sk minus 1 and sk. And I've obtained a solution at the Redal points. So the Redal points are these points here, wherever they happen to be, but they don't include that point right there. Okay? Now, the question is, how accurate is my solution? So what's the state approximation? So the state approximation is capital X k of s, which is equal to the sum from I equals 1 to n sub k plus 1 x k I l I k of s, right? That's my solution. So now I want to know, how accurate is that? Well, one way to determine how accurate this is as follows. And this is actually a fairly good approach, and it works quite well. Is that suppose we compute a new set of LGR points such that, well, I shouldn't say such that. Say new set of, I should be more specific here, new set of M sub k LGR points where M sub k is equal to n sub k plus 1. So all I've done is I've added one LGR point to this whole thing, okay? Turns out that if you do that, this one stays the same, right? Because the first LGR point is always at -1. Turns out that all the others, if I add one, they all shift this way. So that means that the first LGR point on the new set is going to be somewhere in here. The second one's going to be somewhere here, and the third one's going to be here, and it's going to keep going like that. And I'm going to wind up with these points. And then I've got one right there. But that one doesn't matter because it's the same one that I had before. So then what you do is you say, now interpolate x k of s at the new set of LGR points. Okay, so now what am I doing? How am I going to do that? I have two things I have to do in order to do that, right? What is it that I have this state approximation, right? I have these LGR points. I can now interpolate to that new set of LGR points, right? So that new set of LGR points gives me, so let's suppose I do that. Let's suppose I call, so I'm going to say let x, well, let's call them y. Y superscript k of s. Now, I got to be real careful here. Okay, hang on. Before I do that, let me put one more thing down. Okay? So let the new LGR points be denoted S tilde k j, where j now goes from 1 up to m sub k, right? Because that's the new set of LGR points that I've got. I said let m sub k equal n sub k plus 1, right? So what I can do is I can say also let y k evaluated at s tilde j equal x k evaluated at s tilde j. Actually, I don't even need the s tilde. I'll just go yj. Just do this. Y k j. And this goes from j, goes from 1 up to m sub k. All right, does everyone understand this part of the process, what I'm doing here? If anyone doesn't understand this, please tell me. All right? Do you or do you not understand this process? Yes, no, maybe, yes, I do, yes, no, I don't. I have no idea what you're talking about. I'm sitting here, I don't know what you're talking about, but I don't want to say anything, and then later on I'm going to have 500,000 questions because I didn't understand what you were talking about. That's not good, all right? So if you have a problem with this, tell me, all right? All I've done is I've interpolated the solution at this new set of LGR points, right? So if the picture looks like this, engineers love pictures, right? Without a picture, engineers don't know what they're doing, right? So these are the original set of LGR points, right? Here's a good question, all right? What has to be true about these LGR points? This is S sub k minus 1. This is S sub k. This is the original set of LGR points, the ones I've got over there marked with an X. What has to be true? Well, the solution, the coefficients, right, the coefficients of the approximation have to be the values of the state approximation at those points, right? So now if I interpolate to the new set of LGR points, what do I get? Well, here's my interpolant. I drew it like this on purpose because what I plotted here was the actual polynomial. So I've got this interpolant that takes me to these points here, right? So these are the interpolated values. So if you look at this, and there's one here too, right? 1, 2, 3, 4, 5, 6, 7, 8. Actually, there's one here also. So there's one. All right, so now I have these interpolated values. Okay, so these values are these values yj that I have sitting up here. Okay, those are the squares. All right, now, the next thing you do is you say, well, how do I know anything about how good? I still don't know anything about how good the state approximation is, right? All I did was I added one Redal point, and then I interpolated to that new set of Redal points. I have nothing to compare it to, so I have no idea how good it is at this point, right? So the next thing you do is this, is next we interpolate the control to the new set of LGR points. What's the problem with that step? Before you understand why I did it, what's the problem with saying I'm going to interpolate the control to the new set of LGR points?
It might not be optimal. The new control might not be optimal.
Even before that? I have this solution that I just obtained by solving the problem on a particular mesh, right? I have this NLP. I formulated this NLP. I'm solving this NLP. Now I have the solution. What does the solution consist of in each mesh interval? It consists of the state at approximation at all of the LGR points plus the final point, right? But the final point can also be considered the initial point of the next segment, right? And I have the control at all of the LGR points, right? What do I have for the state that I don't have for the control? No. More than that.
The final value.
More than that. You both said the same thing. More than that.
The graph multiplies.
No. I said it at the very beginning when I talked about collocation methods, before I even got into pseudospectral methods, and I bet you don't remember. What have I written on the board so far? Tell me what I've written on the board. I have a state approximation, right? What do I not have for the control?
You don't have a functional approximation.
I don't have a function approximation for the control, right? Because in the process of doing this, I approximated the state, and then I differentiated it, and then I collocated at these LGR points, right? But nowhere in any of that did I ever say that there was a function approximation for the control. I just simply sampled the control at the LGR points, and I treated those as variables in the NLP, right? So what I have is I have sample data. So this is the problem. the control is only sample data. Everyone knows what sample data is? Does everyone know what sample data is? What is sample data? Yeah, but what is true about sample data? I sample a function at a bunch of points. If I tell you that I have a function, but I don't know what that function is, and I sample it at a bunch of points, do I now know the function? The converse is true, though, right? If I know the function, I can sample it anywhere I want to, right? And I don't lose any information because I have the original function, right? But if I never had the function to begin with, and all I give you is a discrete set of values, you cannot tell me what the function is, right? You have no way of knowing what the function was. You'd need to know it continuously in order to know the function, right? So this is the problem, which leads to the fact that the control approximation, or the control function approximation, I'm going to put this in quotes, is not unique. What must be true about the control about any function approximation for the control? So let's just draw a apply. Here's my sample data. Now I'm not going to draw a curve like I did over there. Okay, here's sk minus 1. Out here is S sub k, and that's my last LGR point. Here's my data. I'm going to call these U sub k. That's what I got, right? So what must be true about any function I use to fit this data? What's that? It has to pass through the points, right? So I could use this. I could use this. I could use this. Which one of them's right? They're all right. Which one do I use? There's a. You ever heard the? You ever heard the phrase or the saying? It's called Occam's razor. Do you know what Occam's razor is? Yeah. When you have a choice amongst different solutions, the simplest solution is the one that tends to be the one that's right. So if you had to choose, what would you choose? What's the simplest function? A piecewise linear approximation, right? Is it the right thing to do? Probably not. But given nothing else better to do, you might as well just use a piecewise linear approximation. So we're going to say, assume the control is piecewise linear. It's not a great assumption, but if you've got a reasonable process in place, is piecewise linear, right? If you've got a reasonable process in place, it'll be good enough because once you've converged, once you've gotten an accurate enough solution, it shouldn't matter if you interpolate linearly between the points. It's going to wind up being a pretty reasonable thing. And in fact, they do this a lot. In computational fluid dynamics, this is actually how they generate solutions on different meshes. They wind up interpolating linearly between the points because they don't want to overcomplicate the problem. So they make it as simple as they possibly can. It's like, well, what's the simplest The only thing simpler than this is something that's piecewise constant, right? But piecewise constant doesn't pass through the points, right? So you have to pick something that's at least linear. It can't be piecewise constant, right? So now, we've done that. So now what you do is, now I say let V sub k j be the linearly interpolated values of uk where j goes from 1 up to m sub k. All right? So now I've interpolated these values to the new grid. Now what can I do? Now I have a way of being able to actually do a comparison, right? Which is that if you remember, so recall the following. And I'm going to write this down for global. Right? We know that the solution, well, I'll write it at the original, on the original grid. I know that x2 colon n plus 1, if you want to be technical about it, I can put n sub k plus 1, right? Is that, remember when I did the methods, I actually did everything vectorized, right? Is equal to x1 k, so this is all in mesh interval k, times 1 plus tf minus t0 over 2 times a sub k times f 1 colon n sub k. Now, you remember what this is? I bet you don't remember what this is. I'm going to tell you what it is, but do you remember what it is? Remember when I derived the Redal method, I said that the Redal method can equivalently be written as either a differentiation scheme or an implicit integration scheme, right? This is the implicit integral form of the Redal method in segment k. This should actually be a, yeah, that's tf minus t0 over 2. So this is the implicit integral form of the Redal method. Implicit integral form of the LGR method. But this is on the original grid that I just solved the problem, right? Because I'm using everything here with x and I'm using everything with n sub k. But what you could do is suppose we employ the integration scheme at the new set of LGR points. Now, what we're going to get is, we've got to be a little careful here, okay? What we're going to get is we're going to get y, which is going to be now from 2 to m sub k plus 1. That is going to equal 1 times y1, which is the same thing as x1 because it's the initial point, right? So they're the same. Plus, now I'm going to get this new matrix, tf minus t0 over 2 times this new matrix. I'll call this new matrix, let's call it B. Okay? B sub k times f1 colon m sub k, k. Where this right here, f1 colon m sub k, is equal to the right-hand side f evaluated at y1 and v1 all the way down to f evaluated at y sub m sub k u sub m sub, sorry, v sub m sub k. Okay? So it's a different set of points, right? But it's the interpolated set, right? Because I did all this interpolation. I interpolated that. I interpolated the control. And now I get these values that come out of this, right? But I'm not going to call this, let's not call this y. I'm going to be a little bit more distinct about this. X, Y, Z. It's called z. Okay? Now look what I've got. I have the interpolated values from the original polynomial. I have these interpolated controls, and I've used them to construct the integration scheme on the new set of LGR points, because it's still an LGR scheme, right? It has nothing to do with the NLP anymore, but it's still an LGR scheme, right? So what I've got is I've got the values all the way up to 2 to m sub k plus 1, but I've also got the values over here, and if I actually should have been careful, m sub k plus 1. I've got these values over here. Now, are these values y going to be the same as those values z over there? Will they be the same? Should they be the same? Yes? They should be? Who thinks they should be the same? Who thinks they should be the same but are afraid to say that they should be the same? Because they think I'm going to tell them that they really shouldn't be the same. Do you understand the difference between this value here and that value over there? Yes? Does everyone understand the difference? What's the difference? The difference here is I got this purely from interpolating the state approximation, right? I got these from interpolating the control approximation using whatever approximation I decided to use for the control, which is invariably wrong because I don't know what the approximation is for the control. And then I applied the integration scheme to get the values at this fictitious set of LGR points, which have nothing to do with my NLP, right? My NLP was solved on the original set of LGR points over there, right? So this is an integration based on the interpolation of the control. The other one has nothing to do with that. It's simply just an interpolation of the state itself, right? So there's no way that unless I happen to get the control approximation magically correct and everything matched up perfectly, those values over there are going to match these values over here. There's no way they're going to match, right? So now I have two values of the state on this interpolated grid that I can difference. And I can see how far off they are from one another, right? So now I can see whether or not what the differences are. So now I can compare, so I can write this down here. So we can compare y going from 2 to m sub k plus 1 with z going from 2 to m sub k plus 1 in segment k. If I do that, basically I'm taking the difference, right? I'm taking the difference between them. Now, if I have done this well, it should be the case that these two should not differ by much at all, right? They should be pretty much the same, because if I've solved the problem on a sufficiently accurate grid, it shouldn't make a difference which order I do these operations in. But if I haven't solved it on a very accurate grid, this should not come out to be at all close, right? They should be like way off from one another. So that's the issue. Now, if they don't, let's suppose that I say that I want the tolerance, or I want these two to match within some tolerance epsilon. If they match within some tolerance epsilon, I stop. I'm done. I don't have to ever do anything in that segment again, right? But if they don't, then I have to ask myself the question, I need to modify the segment, right? So let's assume that they don't match, because if they match, then I'm done. I don't have to do anything, right? So let's assume that they're outside of this bound epsilon, meaning the maximum is outside of the bound. So if it's outside of some bound epsilon, what could happen is it could be bad everywhere, right? I mean, I could be outside of the bound everywhere, right? So let's look at the difference. So suppose I let delta equal the absolute value of y minus z. Or I'm just going to abbreviate now because I don't want to keep putting the indices down, right? It's the difference between these two at these points, right? So this delta could look like this. I could have, if here's my threshold epsilon, right? And I could say, well, delta is a bunch of numbers at all these points, right? What could happen is that I could have something that looks like this, where it's satisfied everywhere except for at a couple of points in the interval. That's one possibility. I could also have a situation where it's just uniformly really bad everywhere. So let's suppose I'm in the first case here. Let's mark these with O's. Okay? I'm in this case here where the difference looks like this. So now, what would I want to do if the difference looked like that? I have two choices. I can either cut the mesh, I can refine the mesh by putting in a new mesh point, or I can increase the polynomial degree if the tolerance hasn't been satisfied. Because if the tolerance is satisfied, I'm not in this case. I'm not doing anything, right? I'm done, right? So it has to be that something hasn't met my tolerance, right? So if it turns out that there's a point or a little small region where the error is above my threshold, but everywhere else it's satisfied, what would be the logical thing to do?
Could you group more points in that region?
No. I'm asking you. There are two choices. I either increase the polynomial degree in that segment, or I split the mesh, or I refine the mesh. if I'm in the first case, the one that I've highlighted here with these circles, which would be the right thing to do? Split the mesh, right? Because the error is all right here. It's all in this very small region right here. Everywhere else, the error is fine. So in that case, what you'd do is you'd add a mesh point. And you put a new mesh point right at the point where that peak is. And you'd say, you know what? That's where I have a problem. In the second case, I'm over here where I've got, I'm going to denote these with squares, where the error is uniformly bad everywhere. Or pretty much everywhere. It's uniformly bad. Right? So in other words, the error isn't really any better here than it is over there. They all don't satisfy my tolerance. What would be the better thing to do in that case? Where do I split the mesh? There's no place, there's no preferential spot here to split the mesh, right? Because they're all bad, right? So in that case, you would increase the polynomial degree. So if you're in this case, you refine the mesh. If you're in this case, you increase the degree of the polynomial. And then you take the new set of points that you've decided. Now the question is, how much do you increase the degree of the polynomial? So the issue of increasing the degree of the polynomial is you don't want to increase the degree of the polynomial by much. So the way to do this is to pick a value and say, I'm only going to increase the polynomial degree by that much every single time I need to do it, and make that number really small. So I say, I'm only going to increase it by 1 or 2 degrees, and then solve the problem again. But you don't want to keep doing that over and over and over again. So what happens, because you don't want the matrix to, you don't want this really large polynomial degree. Remember I told you want to limit the largest polynomial you ever use. So you'd have to put a cap on this and say, I'm never going to let this thing exceed 8 or 10. So if it does exceed your cap, then you actually have to go into a third mode, which is I've hit my maximum polynomial degree. I cannot continue to increase the degree of the polynomial because I'm not going to allow it to go beyond a certain amount. Then you revert back to the first case and you say, no matter what, if I've hit the maximum polynomial degree, I'm going to pick the maximum value and I'm going to split the mesh at that point. Even though the error may still be uniformly good, you don't want to continue to increase the polynomial degree beyond a certain point. So you put an upper limit on it and say, I'm going to let the maximum polynomial degree be 10 or 12 or 14 or whatever it happens to be. This is where you get into the artistry of mesh refinement, because it's no longer a science anymore. Now it's about what's the best way that I can do this and still be able to get something that's tractable from an algorithmic standpoint, right? That's a different question. I'm just giving you a framework to be able to do mesh refinement, right? So that's the way you would do this. So those are the two choices. If you increase the polynomial degree, you're increasing what we call p, which is the degree of the polynomial. If you refine the mesh, you're adding a segment, which means you're increasing the number of intervals, right? We call that h. So the combination of doing these two things gives you what's called h and p, which leads to what's called an HP method. It's h if you refine the mesh, it's p if you increase the polynomial degree, and then you wind up, if you do both, or if you allow for both, then it becomes an HP method. Now, if you use something like a Runge-Kutta, like a fixed order method, like a fourth order Runge-Kutta, you never change the degree of the polynomial approximation. It's always fixed at 4. So the only thing you can do in that case is add more mesh points. That's the only option you've got. So that's a purely H method. That's called an H mesh refinement method. If you do what we do in the pseudospectral method when I derived the theory, remember when I derived the theory for pseudospectral methods, I said I was going to do it with a global polynomial, and the only thing you can do is vary the degree of the polynomial? If all you can do is vary the degree of the polynomial, that's what's called a P method. You're not allowing for anything other than I'm going to change the polynomial degree and I'm going to resolve the problem. But if you allow for both, you're in this HP case. And it turns out that this is the area in which people have least studied mesh refinement. Most mesh refinement is done with H methods. They just fix the degree of the polynomial. I'm always going to use a fourth degree polynomial. I'm not going to let it change. And then the theory of pseudospectral methods was derived based on P methods. And the reason it was derived based on P methods is because remember I told you that the Gaussian quadrature integration schemes have this nice property that they converge exponentially as you increase the degree of the polynomial. So the theory is if you have a nice, smooth, well-behaved problem, you should just be able to do this with a global method. You should never need to institute a mesh to begin with. You just use one interval, and then you just increase the degree of the polynomial. Well, that's not very realistic, right? Because as you've seen, there's so many optimal control problems for which things are not smooth, right? You've got bang-bang optimal control problems. You may have problems with singular arcs. You may have problems with other weird anomalies where solutions change really rapidly. And clearly, if you try to approximate that with a reasonably low degree polynomial, you're not going to get very far. It's going to be a pretty bad approximation. So that's why you need to use mesh refinement. And you can't do it with a P method. So at either extreme, if you're going to error on one extreme or the other, you're always better off erroring on the side of an H method. Always. All right? So if I'm not going to allow for the polynomial degree to change, that's perfectly fine. I just fix it at some value, and then I just refine the mesh. And that's all I keep doing is refining the mesh. And the guy who's actually done most work on H method mesh refinement in optimal control is this guy named John Betts. He's got a really good book out, which I'm sure some of you probably have at this point. It's called Practical Methods for Optimal Control and Estimation Using Nonlinear Programming. Fantastic book. Absolutely a brilliant piece of work. It's one of the best books on the subject of optimal control that's ever been written. It's all about practical methods, and it's just incredible what's in there. I mean, it's like an encyclopedia of things to look up in optimal control. And he's done a lot of stuff with H mesh refinement. He doesn't believe in varying the degree of the polynomial. He uses Runge-Kutta or Hermite-Simpson or some really low-order method, and then he just refines the mesh until he's blue in the face. That's basically what he does. So that's his approach. But the problem with refining the mesh that way, and it is a serious problem, is that you can imagine that if you have a problem where you need a lot of intervals in order to get an accurate solution, your mesh refinement scheme is going to keep adding intervals and keep adding intervals. Every time it adds an interval, it has to add yet another set of variables into the NLP which correspond to the collocation of the dynamics in that interval. So your NLP starts to get bigger and bigger and bigger and bigger. Of course, the way Betts deals with it, which is perfectly fine, is that he says, well, what I'm going to do is I'm going to design this really incredible NLP solver that can solve these giant NLPs really, really fast. So he's got this totally slick NLP solver, which he's the only person in the world who can use because it does all these fancy things, and it's really, but I mean, it works really, really well, but it's all kind of integrated into this framework where no one outside of him could actually use it because of the way it's designed. It's integrated in with the optimal control scheme, and it's got other kinds of weird things going on with it. Brilliant NLP solver. It's an incredible NLP solver. And then he could say, I could solve a problem with 1 million variables or 10 million variables or whatever the case may be, right? The problem is that the NLP is getting huge, right? Now, for the average researcher and student and professor and person who's actually solving optimal control problems, we don't have this brilliant, slick, proprietary, I'm going to charge you $50,000 a pop NLP solver, right? Well, nobody has that, right? We have the things that people have available to us in the academic community, things like IPOpt and SNOpt, and things that are free, right? Now, they happen to be very good NLP solvers too, but they're not capable of solving these giant, sparse NLPs of the size that his NLP solver can solve. So in the world in which we live, we want to make the NLP smaller. We don't want to make the NLP bigger, right? So the argument behind using a pseudospectral scheme, of course, is that you should be able to get good accuracy for a relatively small degree polynomial if you use Gaussian quadrature, right? Because Gaussian quadrature converges exponentially if the solution is smooth in a particular segment. So the HP idea comes in from the fact that now what I can do is I can say, well, if I allow for the polynomial degree to change, I may be able to increase the polynomial degree just a little bit and get a lot more accuracy out of just a small increase in the degree of the polynomial rather than continuing to just sort of grossly refine the mesh, just over and over and over again, keep refining the mesh. That'll keep the NLP significantly smaller, and I'll be able to get the same accuracy that I would have been able to get had I refined the mesh over and over and over again with a fixed degree method. That's the key aspect to HP adaptive schemes. So these two concepts of H and P now work together. In the HP method, and you can actually read, there are really good papers, at least in finite elements, on this. The guy's name is Igor Babushka. He's like the legendary guy in the field of field of finite elements. And he's the one who actually originally came up with the idea of an HP adaptive method. It wasn't for optimal control. It was just for differential equations. But he came up with this concept. Now, in the problems that he was interested in, like structural mechanics problems or fluid mechanics problems, you also have discontinuities, right? I mean, in the case of a fluid flow, you could have like a shock wave. You could have some other kind of real, sharp discontinuity, like you cross the sound barrier or something like that, and you get that sonic boom or something like that. So things can happen essentially discontinuously in those kinds of problems as well. And he actually laid out the idea of an HP adaptive method for finite elements for differential equations back in the 1970s. It was a pretty famous sequence of papers that he published. And the idea and the concept of all this is by using the pseudospectral method and taking advantage of its nice exponential convergence in a segment where the solution is smooth, you can reduce the size of the NLP and still be able to get accurate solutions to the problem. Like, here's an example. This is something that you'll see when you actually do it. You remember that Moonlander problem or the double integrator problem that I did, where the solution, the optimal control is bang bang? Well, it turns out that if you do a double integrator with a bang bang optimal control, the second component of the state is piecewise linear, because it says x2 dot is equal to u, and u is piecewise constant. So the first state, if I integrate it, I get something that's piecewise linear, right? If I integrate something that's piecewise linear, x1 dot is equal to x2 in that equation, so x1 has to be piecewise quadratic, right? So if you use a pseudospectral method, you should be able to get that the solution should be a quadratic in phase 1 and the quadratic in phase 2, where these phases define the regions where the control is one value or the other, right? You shouldn't need to overcollocate the problem and have many mesh intervals. Well, if you use an H method, you can't do that, because an H method is going to, by definition, what it's going to do is it's going to keep sandwiching and sandwiching more and more collocation points right at the spot of the discontinuity. And what you're going to wind up getting is you're going to get this large, dense collocation right at the point of the discontinuity, and you're going to wind up overcollocating the problem. You're going to make the problem significantly larger, the NLP significantly larger in size than it needs to be. It needs to be a piecewise quadratic. But you're saying, well, you know what? My method, which is just a very low-order method, all it can do is just keep refining the mesh. It's going to keep refining the mesh, and it's going to keep collapsing more and more and more collocation points right at that spot of the discontinuity. And then you're going to see there are very few collocation points out here, there are very few collocation points out here, and right at the spot where the control becomes discontinuous, you're going to see that there are going to be tons of collocation points right in the middle when you don't need them. And that's the disadvantage to using an H method, is that you're going to wind up making the problem a lot bigger than it needs to be. Whereas with a pseudospectral scheme, you just do two piecewise quadratics, and if your method was smart, it would say, look, I've got the solution. I don't need to do anything to this. I'm done. And it will just stop. And it will just say, that's it. I'm finished. And my NLP is really, really small. You're always better off with a small NLP. If you have a choice, you should always want a small NLP. Okay? We didn't get to the computer, so I didn't get to do that. If you guys want to see some of that stuff, you can come to my office. Okay? We're done for today. So I am going to send the exam out on Sunday. And if you have any questions after I send it out, let me know. But you have several days to work on it, so it shouldn't be a big deal. Okay? All right. Talk to you later.